Alright, so today we'll be doing one of the 5 types of substitution methods you can use in differential equations. It's known as Bernoulli differential equation. You probably know him because probably his maybe his principle within fluids, or like if you learned it like some types of like aerodynamic class or something, the name Bernoulli. So here's the problem. So y squared times the derivative of y with respect to x plus 2x times y to the third equals 6x. So what we want is we want our equation in the form of dy plus dx, dy over dx plus p of x times y is equal to q of x y to the n. So basically what you're doing is you use this when you have some power to the y, I believe, is greater than 1, of course, because 1 will just be linear. So yeah, that's how you're gonna solve. So to get that, we're gonna divide both sides by y squared. So what we're gonna get there is we're gonna get dy over dx plus 2xy is equal to 6x, and it's over y squared, but I'm gonna say y to the negative 2. Alright? So what we want to do is we want to set this to a variable called v, and this v is used on many substitutions. You use it in, I believe, homogeneous. You use it in not homogeneous. I forgot the name of the first method. Let me quickly check. We use it in the obvious one. Homogeneous first order, and then you also use it in the composition obvious. I think it's also used in the other two as well. Yeah, of course, reducible second order and embedded derivative. So we're going to set y. So we set this v thing to, it's similar to the integrating factor, but like it's not exactly the same. But we use this variable that we get to solve the differential equation. So we're going to call this y to the 1 minus n. And it'll make sense why we do y to 1 minus n, because there's going to be a lot of canceling out, and we're going to get it. So they'll be get to the linear first order differential equation, which I outlined in the previous video, where we can use the integrating factor there. So our n variable here, we set y to the n right here, so this is negative 2 right here. So our v is equal to y times 1 times negative 2. That's y to the third. Now we're going to set that y equal to, well, if we want to set y, we just have to root 3 both sides, so we do v to the 1/3. Alright. Then we want to find the derivative of this with respect to x. So this is going to be implicit differentiation. So we're going to say the derivative of this in terms of v is going to be 1/3, just power 1/3 times v to negative 2/3. And then, of course, because it's implicit division, we have to do the variable we use here over dx. Alright? So we have all these details, so we can plug, using these two things we have, we can plug it back into here. So we have dy over dx, so we set that to 1/3 e to negative 2/3 dv over dx, plus we set 2x times v to the 1/3 we said, and we set that equal to 6x to the, we said y to v to the 1/3, but we're going to do v to the 1/3 to the negative 2, so v to the 1/3 negative 2, that's just v to the negative 2/3. So this is perfect, because now, as you can see here, it's the same degree of v both in these two, and that's going to help it perfectly so we can get it to what we want. So we're going to times both sides by something, so we can get only dv dx. So we're going to times it. So we want this thing times some other factor to equal 1. So the coefficient of dv over dx is 1. So that's going to just be 3 times v to the 2/3 You have to times this by two sides and see how it also cancels out here, the v variable in the right side. So this is going to be equal to dv over dx plus 6xv equals 18x. Yeah, 18x. Now this is perfect. This is similar to our homogeneous, how we did it for the homogeneous first. So what we're going to have to do is, instead of treating, because usually it's going to be like p of x, usually the form of that is dy plus dy over dx is this, but instead we're going to be using the variable v. So our integrating factor is going to be e to the integral of p over x dx, so that's going to be equal to e to the integral of 6x dx, and that is, we can ignore the constant, we're going to get e to the 3x squared. So we can times this whole thing by the integrating factor, 3x squared, e to the 3x squared. So we're going to get e to the 3x squared dv over dx plus e to the 3x squared times 6x times v equals 18x times e to the 3x squared. So now we can just say the derivative of that, so we can say our derivative with respect to x of our integrated factor 3x squared times v is equal to 18x times e to 3x squared. We integrate both sides with respect to dx. This will get you e to the 3x squared times v is equal to whatever this integral is. So we're going to have to solve that. I believe you can use integration of parts, or actually no. So we can use up, because the 3x squared times 18x. Let me just write this here, this equation. So if we set u equal to 3x squared, we know that du is equal to 6x dx. So so this is just 3 du, and this is going to just be e to the u. So we just get, this just becomes 3 of the integral of e to the u du. That's just 3 e to the u plus c. So that's just 3e to 3x squared, if we set that to u, plus c, and we're going to have to, we set that equal to, well, this side just cancels, yeah, so we set that to e to 3x squared times v. So we get our v is equal to, we're going to divide e to 3x squared on both sides, so that gets you 3 plus c times e to the negative 3x squared. Alright, so that is our v. And because we know that, we can solve because we know how we use the relation between v and y. So what we did is we set v equal to y to the third. So we can just say this is equal to y to the third is equal to 3 plus ce to negative 3x squared. And the reason we don't want to third root this to say is because of the multiple solutions. Because actually, I think those I'm pretty sure will be different functions, similar to like how y squared equals x is not actually the same thing as y equals square root of x, because it could be negative square root of x as well. So we can leave it in this form, and this should be our answer. We'll check this real quick. Alright, so yeah, so that's how you perform Bernoulli substitution for solving differential equations. Thank you for watching.